Now that we've talked about horizontal and vertical shifting, let's talk about horizontal and vertical stretching and compression. So when does either stretching or compression take place? Well, it takes place when we have, that's a little bit dark, when we have a function that's being multiplied, a function of x that's being multiplied by some number a. And this is an example of vertical stretching and compression. When we have horizontal stretching and compression, we have our x values being multiplied by some number a. And the key difference here is that we have, in this place, we have a number being multiplied by our base function, and here we have our x being multiplied by an a. And this will be more apparent at what the differences are when we do a table and make a graph. But let's just talk about this real quickly. We have, so this, like I said, this is vertical stretching, compression, and this one is horizontal. So let's talk about we'll talk about them one at a time. Let's talk about this vertical one first. So well, let's pick an example function. We'll do y is equal to 1/2 times x squared. And it's key here to notice that the 1/2 is outside the parentheses. So actually, let's write it like this. Y is equal to 1/2 right here. This is an example where it might be a little bit clearer if I do it in function notation. So we'll say that f of x is equal to 1/2 x squared. So in this equation, we're inserting x in for our value. So we get 1/2 times x squared. And this would be a vertical. If we wanted a horizontal, if we wanted to show an example of a horizontal shift, we'd say f of 1/2 x is equal to x squared. And then what we would do is insert 1/2 x in for x. So this is a horizontal. So this is a key difference. In one, we're having the function multiplied by some number, and in the other example, we have the x value times some number being inserted into the function. So again, let's talk about the vertical one first. And again, we have y is equal to 1/2 x. Or again, let's do this in function notation because it'll be easier not to be confused. 1/2 x squared. So the first thing I'm going to do is I'm going to make a table of this and try to explain what is happening with the number values. And then after that, I'm going to take those number values and then make a graph, and then hopefully it will be even more apparent what is happening. So the first thing to do for the purposes of this example will be to make a table of what is the base function, which is x squared. So let's make a table of this. So x values, y values, and this is x squared for x squared. And I'm going to add a few extra values so it's a little bit more obvious. When we get 3 minus 3 squared, that's 9, 4, 1, 0, 1, 4, and we have 9 again. So these are the values if I insert the x, what y do I get for x squared? Now let's do the same thing, but for 1/2 x squared. So we have x and y. Minus 3, minus 2, minus 1, 0, 1, 2, and 3. So we have our values. Now let's make a table out of them. So we have minus 3. And we put this in for the x. We have 1/2 times minus 3 squared. So we get minus 3 squared, which is 9, times 1/2, which is 4.5. So we get 9. We get 3 squared, which is 9, then times 1/2, which is 4.5. And we continue to do this. We put in 2 squared, we get 4. Times 1/2 is 2. We put in 1, we get 1 squared times 1/2, which is 1/2. We get 0, and then we're going to get the same for the positive numbers that we put in. So let's compare these values to these values. Here we put in a minus 3, we get a 9. Here we put in a minus 3, we get a 4.5. So what's happening is, all that's happening is we're getting the exact same values for our x squared function as we normally would here, except we're dividing them in 2. So if we were to continue up this way, we're going to notice that these values are going to equal 1/2 of whatever these values are. I'm sure most people can see that because there's a 1/2. But let's make the graph, and we're going to see that, well, let's first talk about what do you think would happen. Do you think that this 1/2 would stretch the graph or compress the graph? Because if we have, there's two things that can happen. The values can increase more quickly, or it'll take longer to increase. In which case, if these numbers are going up more quickly in comparison to these numbers, it's going to stretch the graph upwards. But here in this case, we have them increasing more slowly at half the rate of this one. So so the graph of this in comparison to this one, it should be compressed, right? Compressed vertically. It's not going to be increasing as fast as this function. This function is going to be increasing more slowly. So what we're going to do is we're going to expect that this be compressed. And we can kind of make up almost little rules. So say we have, for vertical compression, we have y is equal to a times some function. When a is greater than 1, we're going to have stretching. Because when a is bigger, so when there's a number bigger than 1, that means that these values of x, so when I put in 1, I'm going to get something that's greater than 1 if this number was bigger. Say let's put in 2. I get the same number as I would for this one, except it would be multiplied by 2. So instead of 1, I'd have 2. So the y values would increase faster. And as in this case, if we have x is greater than 0, because if we have 0, then we're going to get 0. So we're obviously not going to include 0. But if we have that x is a fraction, that's what this means. If x is greater than 0 but less than, or not a, and not x, I meant a, and less than 1, that means it's a fraction. If it's a fraction, it's going to compress. This is compression. So that's an easy way to tell if you can already know that it's going to be vertical, because this is the way to tell that there's going to be vertical compression. If we have the base function multiplied by some constant value, and if that value is greater than 1, then there's going to be stretching. And if that value is greater than 0 but in between 1, it can be a negative one. That would just, we'll talk about that later. That would mean that there's a reflection. But let's forget about negative numbers for now. And let's just say that if x, or if a is some kind of fraction, that means there will be compression. And that's why I chose this example, because I didn't want to have a huge graph. So let's now look at the graph. So let's first graph our normal function. So let's first graph x squared, so we can compare it to the other one. So let's first graph x squared. It starts at 0, 0, it goes to 1, 1, and minus 1, 1. It's symmetrical. So then it goes to 2, and 1, 2, 3, 4. So 2, 4, minus 2, 4, and it goes to 3, 9, which is off of my graph. So we'll just draw like this and say that it goes, oh man, that suck. Man, I don't know why I suck so bad at drawing. There we go. Oh man, well, that's close enough. I mean, you guys have seen a parabola enough times by now, I'm sure, to know what the graph of x squared looks like. So now we have the graph of x squared. Let's graph 1/2 x squared. So here's another graph. We're going to graph 1/2 x squared. So it started out at 0. And remember, it's going to be 1/2 of, remember what we noticed, that this graph was exactly 1/2 of what all these other values are. So when we had 1, we had a half. So we had 1, we had a half. So it's right there. And we're going to get minus 1, we're going to get minus a half. And we had 2, instead of getting 4, when we put in x is equal to 2, instead of getting 4, we had 2 instead. And same thing with the minus. And when we put in 3, we didn't get 9 like in this graph, which is off the chart. We got 4.5. So that's right here. 3 minus 3, 4.5. So you can see that this goes up much more slowly. See, it's like they look exactly the same, but this parabola is much wider than this one. It's vertically, we say that it's vertically compressed. But it's if we expanded this out into infinity, it'd be much, much easier to see. Or with a different function, it would be much easier to see the compression. But also, it's just I'm very bad at drawing too. Or if we picked 1/4 instead of 1/2, the compression would be more pronounced. So the larger, or the smaller this fraction is, well, the larger number in the denominator said we had 1/10. Then it would be even more pronounced. Instead of 1 minus a half, we'd have 1 times minus a tenth. That would be all the way down here. And then when we put in x is equal to 2, instead of getting 4, we'd get 1, or we'd get a 10 over 4, which is 1/5. Is that right? Yeah, no, 2/5. Yeah, 2/5. Sorry about that. Yeah, so we get 2/5. So, I mean, we've hardly moved at all. So we'd be, so if we had put in 1/10 instead of 1/2, we'd have been at 1/10. Who knows? That's like all the way down here somewhere. And when we put in 4, we would have been at 2/5, which is, or if we put in 2, we would have been 2/5 instead of 4, which would have been like right here. It's like below half. And then when we put in 3, instead of getting 9, we would have gotten 9/10, which would have been, right here at 1. So you see how slowly this one would have gone up. I mean, it probably would have gone up something like this. So extremely slowly. And then the other side. So this would have been y is equal to 1/10 x squared. So you can see that it's been pushed downwards, like somebody sat on top of it or something like that. So that's the basis of this. And again, let's talk about if it had been greater than 1, if it had been 2x squared. Then instead of 1, or I'll do a different color. So if we had 2x squared, when we put in 1, instead of getting 1 squared 1, we would have gotten 2. And when we put in 2, instead of getting 4, we would have gotten 8. So we would have already been all the way up here. So it would have looked like this. So it would have been stretched vertically like that. So that's vertical stretching and compression. Let's talk about horizontal stretching and compression now. And we're saying that horizontal stretching and compression happened when we had some function x. It's easier to see like this. So if we have some number ax, so a times x into some function, so y is equal to f of a times x. So if we do the same equation, let's do the same thing. Let's put in a as 1/2. So we have y is equal to, or let me do this in function notation again. So we have f of 1/2 x is equal to 1/2 x squared. So in this case, instead of multiplying the function times 1/2, so when we had vertical stretching, we had y. Delete that back. When we had vertical stretching, we had y is equal to a times some function of x. In this case, we had y is equal to some function of x, where the x is being multiplied by something. So if f of x is equal to x squared, that means y is equal to, this is for vertical stretching, y is equal to a times x squared. And in this case over here, where we have horizontal, y is equal to 1/2 x. Oh man, that's written out. So y is equal to, and this is for horizontal, y is equal to 1/2 x squared, where the 1/2 is being inserted with the x into the equation. That's what I'm really trying to bring across here, is that the 1/2 is being put in with the x. So wherever you see an x, instead of putting x, you put 1/2 x. That's what the distinction between horizontal and vertical is. And sometimes it's not really explained, or it's just not given enough emphasis, in my opinion, in the books anyways. So let's talk about this vertical. So as we said, we have f of 1/2 x is equal to 1/2 x, and both of them are being squared. So let's make a table for this and try to figure out what's going on. Again, I'm going to make a very fast table for the base function so we can compare it. So -3, -2, -1, 0, 1, 2, 3, 9, 4, 1, 0, 1, 4, 9. And this is x squared. And here we're going to have again our function f of 1/2 x is equal to 1/2 x squared. Or you can write it like this. But I like writing this in function notation because it's easier to see that we're not putting in x for the equation, we're putting in 1/2 x for the equation. And this makes it very, very clear. Some people might just leave the 1/2 outside the parentheses, and that's not a horizontal, or that's not a horizontal compression, that's a vertical one. So you're doing the opposite. But now I don't have that much room. But anyways, let's do x, y, -3, -2, -1, 0, 1, 2, 3. So in this equation, we're doing this. So we put in -3. That's 1/2 times -3 squared. So that's equal to -1/2 squared, which is 2 1/4, I believe. Is it? Yeah, 2.25. So this is equal to 2.25. If we put in 2, so we have y is equal to 1/2 times -2 squared. And you can square this beforehand, but you're going to get the same answer. I like multiplying them first and then squaring them. But anyways, here we have 1/2 times minus 2. 1/2 times minus 2 is minus 1. So we get minus 1 squared, which is 1. So 1, if we put in minus 1, it's minus 1 squared, we're going to get minus 1/2. Minus 1/2 squared is 1/4. So 1/4. And then we're going to get the same thing. We're going to get 0, 1/4, 1, and 2.25. So here, this is sometimes a little bit more difficult for some people to understand why this is causing a horizontal stretching or compression. But basically what is happening here, it is as if we're taking the function value of a different number. So if you look, let's say, this is the easiest example to do. So if we do y is equal, or if we substitute x in as 2, so we do 2 times 1/2, and as we saw earlier, we got 1. But 2 times 1/2 is 1, so it's as if we're putting in 1 instead. So if it's like we're solving for 1 of the normal function. So if we go over to 1, because 2 times 1/2 is 1, but the x value is 2. But since we're multiplying it by a half, it's actually like we're solving for x is equal to 1. So let's go over to x is equal to 1 over here. And we're going to notice that y is equal to 1. And that's equal to our 2. We'll do that in a different color. But the reason this is because we're multiplying it by a half. But we're actually solving for f of 1, or x is equal to 1. Although we're getting the answer as if it for 2, though, because we're multiplying it by a half. So it's like this function is solving for half of whatever this would be. So if we put in, when we're solving for 1 for this equation, it is as if we are solving for 1/2 of this equation. So if we put in 1/2 to this original equation, we get 1/2 squared, and that's equal to 1/4. And we go over to here, and that's what we got over here, except we got it for 1, because our values are being multiplied by 1/2. If this number was, let's say 1/10, we would basically, let's say it was 1/10 and we were solving for 2 again, and we'd get 1/5. So we'd get 1/10 times 2, or let's do 1/10 times 2, which would be 2/5, and then we would square that. And then whatever that answer is, it would be the exact same value as if we had solved for 2/5 over here. So it's like we're changing what values, that's basically what this multiplication is doing, is it's changing what y values we're solving for. It's shuffling them around a little bit. It's altering them by whatever we're multiplying it by. So that's what's causing the compression, the horizontal stretching and compression. Well, now that we've seen what these values have done, the y values have gotten smaller, so it's taking them longer to go up. So would that be compression or stretching? From a horizontal point of view, it would actually be a stretching, because it would take, if it takes longer for the y values to increase, then it means it's stretching sideways. If they increased faster, then it would squeeze it sideways. So the opposite is true when the number we're doing multiplying. So when we have horizontal, and that's when we have y is equal to f of a times x. when a is greater than 1, it compresses the graph. It compresses it, and it compresses it horizontally. If we look at it from a horizontal perspective, if we have some graph and it's increasing faster than the original function, see, because if this was, instead of multiplying by half, we were multiplying by 2. That means instead of 2 times 1/2, in each case it's like we're solving for 1 of this function, we'd get 2 times 2, which is 4. So it would be like we were solving for 4 for this function. So let's do that. Let's do a real quick example. So instead of multiplying, let's say instead this function was 2 times x squared. Let's say it was this instead. What we'd be doing, and we put in 2. So we put in 2, we'd get 2 times 2 squared, which is 4, and 4 squared is 16. But if the value for this being 4, it's just x squared. So it's just 16. That would be the next value on this graph. So we'd see that for 2x, its 2 value is the same as this one's 4 value. So it's getting higher y values faster. So it's making the graph increase. So if this is the normal one, so if this is just x squared and this is 2x squared, it is being compressed inwards. So that's why we say when we're dealing with horizontal stretching and compressing, when a is greater than 1, it compresses. And then when a is in between 1 and 0, it stretches it. And we'll see that when we graph this next example. Let me scroll down. Okay. So let's put the original one on. So we have 0, 0, 1, 1, minus 1, 1, 2, 4, and 2, minus 2, 4. And then we have 3, 9 as well, but it doesn't fit on the graph. It goes up too fast. Oops. Did not mean to do that. Oh, that didn't turn out half bad. Alright. Alright. Well, let's look at our table of values real quick. It started out at 0, 0. Just like the other one. And then we had 1/4, 1, and 2.25. So we had 1 and 1/4. So that's like all the way down here somewhere. Minus 1, 1/4. And then we had 1 and 2.5. Yeah. 1 and 2.25. And we had 2 and 1. And then 2 and 1/4. So there's 2, let's just say that's 1/4. 3, 2 and 1/4. So we can see that this graph has been stretched horizontally in comparison with this graph. If it had been 2, instead of, let's say if we had y is, so here is y is equal to 1/2 x squared. If we had y is equal to 2x squared, it would compress the graph because it would be going up more quickly. It would be going up really fast like this. That looks too much like the eye. It'd be going up really fast. It'd be like this. It'd be much narrower because the values would be increasing much more quickly. And this is the opposite when we were dealing with vertical compressing. So here, well, pretty much the same thing's happening. In this case, the graph widened as well when we did 1/2. But when we look at it vertically, it's being compressed vertically. It's like when you sit on top of something, if you look at it from a vertical perspective, it's being compressed. But if you look at it from a horizontal perspective, it's being stretched. So the same thing is happening both ways, but So that's how it's easier to remember. Just think about somebody like a garbage compactor. When you're thinking about if a fraction or a number is going to compress it or if it's going to stretch it. Because when we multiply by a fraction, it's always going to stretch it out widthwise because it's going to be increasing more slowly. Either way. But when we're looking at it from a vertical perspective, we're saying that it's being compressed because somebody's sitting on top of it. And then when it increases faster, we're saying it's stretched vertically. But here, since we're looking at it from a horizontal perspective, we're saying that it's stretching. But if we look at this from a vertical perspective, we can say that if we look at it from a vertical perspective, it would also be being compressed. It would be being compressed. But we're looking at it from horizontal this time. So we say that it's being stretched. So that's something to make sure you don't get confused on. The exact same thing's happening. It's just it seems to have switched, although it hasn't. It's just the way we're looking at it has changed. Instead of looking at it vertically, we're now looking at it horizontally. And if we're talking about it horizontally, then it is stretching. But if we're talking about this vertically, then we would say that it's being compressed. So that's the only thing really that you should take care to make sure you don't say something wrong, I guess, or because a lot of the times now, once we know the fundamentals of what causes compression and stretching, it's not really necessary for us to graph it out. We say, oh, here we have something being multiplied by an x. It's being inserted into the x value. So therefore, this is a horizontal change, or this is going to change it. It's going to change horizontally. It's going to compress it horizontally because it's going to increase faster. And likewise here, we can see here, we have a constant being multiplied by a function. So if we we take that to be a vertical compression or stretch. And since this one was a fraction, it's going to be a vertical compression because somebody is sitting on our graph and crushing it and flattening it out.